Howdy. So what happens if you put ice outside on a nice warm day? The water molecules absorb that heat and that becomes kinetic energy. Eventually the molecules have high enough kinetic energy to partially overcome the intermolecular forces, and so you go from the solid ice to liquid water. Is there another way of thinking about it? Well, ice is the most stable phase of water below 0 degrees Celsius. Between 0 and 100 degrees Celsius, liquid is the most stable phase. Above 100 degrees Celsius, the gas is the most stable phase. All systems tend toward the most stable configuration, the lowest potential energy. And so this video is on the most stable configuration of a system. Again, all systems tend to the lowest energy, the most stable configuration. Equilibrium is just about what is the most stable configuration of a system. Understanding equilibrium is essential for understanding chemistry. The next 4 chapters of Chem 114 are just on equilibrium. Today's concepts can be applied to chemistry, physics, biology, economics. All systems tend to the most stable configuration in the long term. So after watching this video, you should be able to relate the following parameters to each other qualitatively and quantitatively. Change the entropy of the universe, change the enthalpy of the system, change the entropy of the system, change the Gibbs free energy, and equilibrium constant. You should identify the similarities and differences between the reaction quotient and the equilibrium constant. You should be able to write down expressions for both the reaction quotient and the equilibrium constant. You should be able to determine the reaction quotient for a reaction. You should be able to determine how a system will reach equilibrium. Given the relative values of Q and K, you should be able to determine if the forward or reverse reaction is faster. You should be able to determine the concentrations at equilibrium, and you should be able to identify characteristics at equilibrium at the macroscopic level and at the atomic level. And so we've talked about 3 laws of thermodynamics. The second law, my favorite, says that every spontaneous change increases the entropy of the universe. Again, in this context, spontaneous does not mean instantaneous, just means occurs without any outside intervention. We saw that the best way of thinking about entropy is poor Dr. Boltzmann's equation. Entropy is equal to Boltzmann's constant times the natural log of W, where W is the number of configurations. And so more configurations leads to higher entropy. Now, the second law is very powerful. You can determine what's going to happen from it, but it's kind of daunting because you have to know, how does the entropy universe change? Well, if we think about the universe is composed of a system and a surroundings, and we'll define it as a closed system, so the only thing that transfers between system and surroundings is heat and work. That means the change entropy of the universe is equal to change entropy of the system plus the change entropy of the surroundings. Now we define it such that, again, the only thing that affects the surroundings is heat and work. And so if you add heat to the surroundings, its entropy will increase. If you take heat away from the surroundings, transfer it to the system, then the entropy of the surroundings will decrease. And so the entropy of surroundings, the change entropy of surroundings, is equal to minus delta H over T. If delta H is positive, that means heat's going from the surroundings to the system, and so the entropy of the surroundings is decreasing. Now if we take this equation, we'll multiply through by minus T, we get this, and now we can define minus T delta S universe as equal to Gibbs free energy. And so that gives us delta G equals delta H minus T delta S. And so it's kind of cool. All these parameters are in terms of the system. So we started worrying about the started worrying about the universe according to the second law, and we broke everything down into the system by assuming that we're talking about a closed system. And so the only thing that affects the surroundings is heat and work. Now, because delta G equals minus T delta S universe, for spontaneous processes, delta S universe is positive, which means delta G would be negative. Now we can think about delta G in terms of potential energy. And so if you're going from high potential energy to low potential energy, that would be negative delta G, because remember, it's going to be products minus reactants, and that would correspond to a spontaneous process. And so we can calculate delta G as minus T delta S universe, or we could also do products minus reactants. Remember, Gibbs free energy, enthalpy, and entropy, they're all state functions. And so for all of them, you could do products minus reactants. We could also calculate delta G by delta H minus T delta S. And so if we plot the free energy on the y-axis and reaction quotient on the x-axis. And so on the left-hand side, we have only reactants. On the right-hand side, we have only products. And in the middle, we'll actually have a mixture. And so here, the products have higher potential energy than reactants, so the products are less stable. And so our delta G is actually going to be positive, because again, products minus reactants. And so that would correspond to a positive delta G, which would be a negative delta S of the universe. And so that would be a non-spontaneous process. And at equilibrium, we'll have mostly reactants. If the products have lower potential energy, again, delta G is products minus reactants, your delta G would be negative, which would correspond to delta S universe positive, and that would correspond to a spontaneous process. Now, the x-axis is the reaction quotient, and that's just going to be the concentration of the products divided by the reactants, and the coefficients for the reaction become exponents. Now, you can imagine that if we drew a line from the reactants to the products, maybe that would be what the free energy was like, but because in the middle you have mixture, which is going to give you a higher entropy, lower Gibbs energy, that's what caused this minimum. It's going to be somewhere in between pure products and pure reactants. And so this minimum is the lowest free energy. It's the most stable configuration. It's where the system is going. And so if we start with just reactants, the reaction will proceed until we get to here. If we start with just products, reaction proceeds until we get to here. No matter where we start on this surface, we always end up at the most stable configuration, the lowest energy. And so when the system's at the most stable configuration, Q, the reaction quotient, is equal to K. Remember, reaction quotient changes as the reaction proceeds. K, the Ekman constant, defines the most stable configuration for a system. The Ekman constant is a constant for a specific reaction at a specific temperature. And so here we have the iron plus the thiocyanate going to iron thiocyanate. And we can imagine, okay, what happens if we start with just reactants? What happens if we start with just products? What happens if we start equal concentrations of everything? Now, if you notice, for equilibrium, often use these two arrows, meaning that we can have the forward reaction and we can have the reverse reaction. Also notice above these plots, there is another plot where the y-axis is Q and then the x-axis is time. And so if we start with just reactants, our Q is 0. And then as the reaction proceeds, Q increases until Q equals K, which corresponds to equilibrium. If we start with just products, Q is going to start at infinite. And then as the reaction proceeds, Q goes down until eventually Q equals K. If we start with equal concentration of all three, eventually it still gets to equilibrium. And so again, no matter where you start on this curve, we'll always get to equilibrium. So if we start with all reactants, reaction proceeds until we get to here. If we start with all products, the reverse reaction proceeds until we get to there.
Initially, only complex formation is possible. As the product concentration increases, the dissociation rate increases until finally both rates are the same.
And so if we start with just reactants, eventually we get to here. And so we can actually calculate, these are initial values. And then actually, as the reaction proceeds, eventually we get to these concentrations, which would correspond to Q equal to K. If we start with just products,
initially, the dissociation rate is faster than its formation. As the reactant concentrations increase, the rate of formation increases until finally both rates are the same.
And so again, no matter where you start on this line, you always end up at the most stable configuration. And so Q is the reaction quotient. It was the x-axis. It's products or reactants. Coefficients become exponents. It can be defined at any time we use it to monitor the reaction. K is the Ekman constant. It's also products or reactants. Coefficients become exponents, but it defines the most stable configuration. K, the Ekman constant, is a constant for a specific reaction at a specific temperature. And so if Q is less than K, that means there's more reactants than at equilibrium, and so the forward reaction should be faster. If Q is greater than K, you have more products than at equilibrium, and so the reverse reaction will be faster. If Q equals K, then the rate of the forward reaction equals the rate of the reverse reaction. And so Q and K, products or reactants, coefficients become exponents. And so if we look at this one, we have 5 times CO2. And so we see this 5 becomes this 5. 6 in front of the water vapor becomes that 6. 8, 8, etc. Remember, the stuff on the right is always the products. Stuff on the left is always the reactants. It's a little confusing because you could have the forward reaction or the reverse reaction, but the stuff on the right is always the products. The stuff on the left is always defined as the reactants. Now, pure solids and pure liquids are not listed in reaction quotients or equilibrium constants. Their concentrations are treated as one. And so here we have liquid water going to water vapor. And so we do products over reactants. But because that L, that concentration is just going to be 1. And so pure solids and pure liquids do not appear in properly written equilibrium expressions. And so for this reaction, you would just have K equals concentration of water vapor. And again, you can kind of think about it as a valley with a boulder. So Q defines the current position of the boulder. K defines the final position of the boulder. No matter where you start the boulder, it always is going to end up at the minimum. And so the minimum, the most stable configuration is when Q equals K. And again, K is a constant for a specific reaction at a specific temperature. And so if Q is less than K, then we know the reaction will go from left to right. The forward reaction will be faster than the reverse reaction. If Q is greater than K, means we have more products than we should at equilibrium, and so the reaction will go to the left. The reverse reaction will be faster than the forward reaction until we reach equilibrium when Q equals K. And at equilibrium, the rates of the forward and reverse reactions are the same. So true or false, the higher the chemical potential energy, the more stable the system. And that would be false. The higher the potential energy, the less stable the system. Which of the following is true for spontaneous reactions? And so for spontaneous, that means delta S universe is positive, which would mean delta G is negative. Spontaneous means that the products are lower energy, more stable. And so at equilibrium, you'd have mostly products, so K would be greater than 1. Because again, K and Q are products over reactants. And so there will be mostly products at equilibrium. That is true. The reactions have lower chemical potential energy than their products. That one is false. For spontaneous processes, the products have lower energy, are more stable. And so we can think about equilibrium macroscopically. And so once the system reaches equilibrium, it seems like the system is static, nothing's changing, the concentrations are constant. But at the atomic level, the reactions are still occurring. It's just that the rate of the forward and reverse reactions are the same.
When a solution of iron 3 nitrate is added to a solution of sodium thiocyanate, the red-orange iron thiocyanate complex ion is formed. Although the reaction looks complete, substantial amounts of iron ion and thiocyanate ion remain unreacted in solution.
And so again, it looks like nothing's changing. Macroscopically, at equilibrium appears static, but you still have the forward rate and the forward reaction, reverse reaction. It's just that the rate of the forward reaction equals the rate of the reverse reaction, and so that's why the concentration does not change.
When iron 3 ions contact thiocyanate ions in solution, they can react to form a complex ion, iron thiocyanate. As the reaction proceeds, product molecules can react in the reverse direction to separate and reform the original ions. Eventually, the concentrations of products and reactants become constant. At this point, the rates of the forward and reverse reactions are equal, and the system is in a state of dynamic equilibrium.
And so when Q equals K, that means you got less product than at equilibrium. And so we know the reaction will go from left to right. And the way that happens is if the forward reaction is faster than the reverse reaction. If Q is greater than K, it means we have more product than we should at equilibrium. And so some of the product will be converted to a reactant. Now it can go from right to left by the reverse reaction being faster. If Q equals K, that's the most stable configuration, and so the concentration is not going to change because the rate of the forward reaction equals the rate of the reverse reaction. And so for a simple reaction of A going to B, and so say we start with just A, and so as the reaction proceeds, the concentration of A goes down, concentration of B goes up, and eventually reach equilibrium, and so the concentrations no longer change. Now, if we look at the rates of the forward and reverse reaction, so the rate of the forward reaction actually goes down because the concentration of the reactant goes down. The rate of the reverse reaction goes up because the concentration of the product is increasing. Now, at equilibrium, the rate of the forward and reverse reactions are equivalent because the system is no longer changing. The reactions are still occurring. It's just that the rate of the forward reaction equals the rate of the reverse reaction. And so please remember, Q is reaction quotient. We can define it at any time. We use it to monitor the reaction. K is the Ekman constant. It's a constant for a specific reaction at a specific temperature. If we know the relative values between Q and K, we know how the system will reach equilibrium. If Q is less than K, more products will be formed. If Q is greater than K, more reactants will be formed. The system always tends to lower its energy. I hope that helps.